When an acidified solution of sodium nitrite is added to aqueous potassium iodide, iodine and nitrogen monoxide NO are formed. To give the oxidation states of nitrogen in the following species. Okay, so this one has got to add up to -1. That's that bit there. I've got 2 oxygens at -2 each, so that's -4, which means that the nitrogen here must be +3 in order for the -4 to make it equal -1. So N is +3. So with this one, the nitrogen and the oxygen added together must equal 0. 1 oxygen at -2, which means that the nitrogen must be +2 in order to make that neutral. Okay, part B. Write half equations for the conversion of NO2 minus in acidic conditions to NO. The acidic conditions is basically H pluses, which will be added when we balance this. So follow this through the rules. So start with the oxidation state, the oxidation elements. So I've got 1 nitrogen here, 1 nitrogen there, so that's all fine. I've got 2 oxygens on the left, 1 on the right, which means I need water. So I've just added 2 hydrogens on the right, which means I need 2 hydrogen ions on the left. So that's that acidic solution I was on about. The right-hand side is neutral, which means for the left-hand side to be neutral, I need to add 1 electron to that. Part C, write a half equation for the conversion of I- into iodine. So again, the redox elements start with that. So I need 2 iodides to iodine, and then I need 2 electrons over here. The overall equation, so I just need to make sure that the electrons here and here balance, which at the moment they don't. So I'm just going to go through and double everything in here. So that becomes 4, 2, 2, and 2. So when I bring these 2 equations together, now that the electrons balance, I've got 2 NO2 minus plus 4H plus 2 I minus, the electrons cancel, which then gives me iodine plus 2NO plus 2H2O. So the role of NO2 minus in the reaction, so we can get this from here. If we look at what is happening here, so the oxidation is reducing, which means that the nitrogen in the NO2 minus is itself reducing. So if it is itself reducing, that means that it must be an oxidizing agent. Okay, a solution of nitrite ions reacts with acidified chlorate 5 according to the following equation. 25 centimetres cubed of sodium nitrite. So 25 centimetres cubed of sodium nitrite required 27.4 centimetres cubed of a solution of a 0.02 solution of potassium chlorate 5 for complete reaction. Complete the concentration in grams per decimeter cubed. So I need to get the concentration of the sodium nitrite, that's this bit here. So I need the concentration of that first in moles per decimeter cubes. This is a mole calculation. So I'll start, there's only one I can actually start by working out with, and that is the potassium chlorate. So the number of moles of the chlorate is concentration times volume. So the concentration is 0.02 times 27.4 times 10 to the minus 3. So if I work all that out, that gives me 5.48 times 10 to the minus 4. So from there, using the ratios, I can work out the number of moles of NO2 minus. So it's a 2 to 5 ratio. So to my 5.48 times 10 to the minus 4, I divide by the 2 and then multiply by the 5, which gives me 1.37 times 10 to the minus 3. So I've got the number of moles. Now the volume is going to be so 25 centimetres cubed. Right, okay. So concentration of NO2 minus is number of moles divided by the volume, and the volume in the question is 25 centimetres cubed. Don't forget to do times 10 to the minus 3, so it's in decimetres cubed. That gives me a concentration of 0.0548. Now that's moles per decimetre cubed. And when we go from moles per decimetre cubed to grams per decimetre cubed, I hope you can see that the only thing that's changing here is moles to mass. Okay, the per decimetre cubed is the same. So all I need to do here is multiply this by the MR. So the concentration of this then is 0.0548 multiplied by the MR. So 2 16s plus 14, that's 69, which equals, now this is in grams per decimetre cubed, 3.78 grams per decimetre cubed.